Yeah, might as well get started. First of all, this is the last talk in the C-PREE David Bradford series on policy research in energy and the environment. And so after this presentation today, happy holidays. We'll see you again in the new year. But yeah, we are fortunate today to have David Budescu with us. David Budescu is a psychologist. He's in fact the inaugural Anastasi Professor of Psychometrics and Quantitative Psychology at Fordham University. He got his undergraduate degree in psychology and statistics at Haifa University. Then got his PhD in 1980 at the University of North Carolina in Chapel Hill in quantitative psychology with a minor in biostatistics. Then actually worked a couple of years at the Research Triangle Institute. Went back to Haifa for an academic career for 10 years. Spent 16 years at the University of Illinois in Urbana-Champaign, where actually I first met him, I think. And then since 2008, he has been at Fordham in quantitative psychology. And yeah, he's one of the few psychologists, I think too small a group of psychologists, who's interested in applying sound psychological theory and also solid methodology to important real-world problems, real-world social problems. And has been working for over 30, almost 40 years, sort of on how to communicate uncertainty in numerical and in quantitative ways, and also verbal ways. And I think sort of more recently has applied some of his insights to the communication of such uncertainty in the IPCC process. He has numerous awards, and he is a fellow of different societies, American Psychological Society, American Psychological Association. He was president of the Society for Judgment and Decision Making, numerous publications. He's a new incoming editor of the journal Decision, which is sort of specializing on quantitative approaches to decision making. But I think sort of rather than describing his research, we let him talk for himself. And please help me to welcome David Budescu.
Thank you very much. Thank you very much for the kind introduction and for the invitation. And it's a pleasure and an honor to be here. And I'm very grateful for the opportunity to tell you a little bit about the work that I've been doing. So I want to start with a few explanations, clarifications, apologies, whatever way you want to take them. So the two key words in the title of my talk are climate change and uncertainty. And it's quite obvious from Elke's introduction that I'm not a climate scientist. In fact, I am a person who works in judgment, decision making, and for being interested in the impacts of uncertainty on individual and group decision making for a long, long time. And I've kind of stumbled into climate change about 10 or 12 years ago, and some people asked me to collaborate on some issues. And I think, so the point is that I'm looking at it from the general perspective of uncertainty, and climate change is just one other instance among many others in which uncertainty plays an important role. But I want to say, and I'll kind of give some details later, that if someone wanted to design a prototype of what exactly does it mean to deal with deep uncertainty, the most complicated and most convoluted ways, you couldn't come up with something that is more than climate change, because it incorporates a variety of features that make it special and unique. And I think it's a fascinating fascinating facet of uncertainty to study and to try to contribute to. The second apology is that I've had this experience several times before, and I'm sure Elke had before, where in one of these climate science meetings, depending on the size of the group, I'm either the only social scientist or one of two or three, and people talk about the models for 2 or 3 hours and say, well, how am I going to put this into a nice paragraph or one graph to communicate it effectively? And everyone gets quiet, and they all point at you. You must have all the answers. So I need to explain ahead of time that I will not have that magical answer. I will not have that magical list of things to do and things to necessarily avoid. I'll have at the end possibly a semi-serious list of recommendations. But I think that neither I nor I am afraid anyone else has mastered and basically put together that kind of list of general principles that will solve all the problems. The other thing I want to say is that instead of presenting, here's the theory and a model, and I'm going to one step after the other. This will be really a presentation of a collection of 3 or 4 type of studies that we've done over the years. Each one of them illuminates a particular point I'll try to make. So that makes the talk modular, so to speak, so I can stop at several points. And I think it's my preference, if you don't mind, rather than waiting the very end with questions, feel free to interrupt me at any point. I will not be, there'll be absolutely no pressure in the sense that I will not be able to finish because I'll just skip one of the sections. So what I want to do is to explain why I think climate change is special. Then I'm going to talk about 3 things. This issue of whether is there such a thing as universal imprecision aversion, as some people are suggesting. I want to deal with the issue of the varieties of type of uncertainty and show how not all uncertainties are interchangeable and the like or treated identically. I'm going to talk about a little bit about the work that Elke alluded to about how to communicate uncertainty in the IPCC reports, and then I have some recommendations. So the first thing I want to talk about is really what is special about climate change and what makes it so hard for people. And I don't mean it in a very crude sense, that you see these surveys that come up periodically. 60% people believe it's true and 20% don't, and so on and so forth, whether people believe or not. But it's really in a deeper sense, that when you ask people attitudes, concerns, and so on, climate change as a general topic does not occupy as high a place in their thinking, in their concerns for the future, as I think most scientists think it should. In other words, there's a disconnect between people's perception of what are dangers, or problems facing us as a society and the scientific world. And I think that one point I want to make is that really, from a psychological perspective, it's a very difficult topic to digest and to internalize and accept. So this is from a recent chapter that we wrote for, I think, the Oxford Handbook of Climate Change Communications, kind of the key things that from that chapter. So psychologically speaking, climate change is construed as perceived as being psychologically distant. It is global. Its full impacts are not now, are going to be way out in the future, if at all, because it is uncertain. And it also, the way it will impact people is not going to be universal and uniform, but it's going to be very differential. It's going to affect different people at different times in different ways, and to some people it may even have beneficial effects. I mean, one small secret that no one wants to talk about, that there are lots of nations that benefit from climate change in ways that make it, in fact, against their own interest, would rather see many of the impacts of climate change. So much of people's perception and experiences are driven by personal experiences, and contrary to what I said about climate change, all the personal experiences are local, are immediate, they're in the present, and they are driven by the weather rather than the climate. And so that drives a lot of the people's thinking. There's a very nice line of work about local warming, which basically shows very nicely that when people are asked about climate change in days which are either much warmer or colder than expected in a particular location at a particular time, that can push their perceptions by 5 to 10 or even more. In other words, it's extremely difficult to ignore that. So for most people, climate change is abstract, high level, and it doesn't have any, except for very, very special circumstances, the affect and the urgency that other concrete representations have. So, a very vivid example is during Sandy, it was now 10 years ago or 8 years ago, where I live in Midtown Manhattan, in a high-rise, and all the experiences are between neighbors are in the elevator. For about a week, that's the only thing people were talking about on the elevator. But so that was vivid, it was immediate, it was very, very, it drove everyone's thinking, and then it disappeared. It's sometimes very hard to even determine from a psychological individual perspective whether something is indeed related to climate change. This is a problem from the scientific point of view, although now there is a methodology to determine not whether something is caused by climate change or not, but to determine the degree to which this is more likely to have happened because of climate change rather than under normal circumstances. But I think to even determine in your thinking, is this climate change related, is a very, very tricky problem. And you usually don't get the feedback that will allow us to say yes and no. There's an interesting side result in many of our studies that we administer a lot of questionnaires, and one of them has to do with simply, did you experience climate change? So in other words, what's your level of personal experience with climate change? And you don't have to make anything action or what do you think it's strong, or simply have you seen detected changes? And when you look at the results, on average, Republicans compared to Democrats, they report that their personal experience of climate change are much, much lower than others. So in other words, people who live in the same environment experience the same physical reality, but when they code it and they basically classify it for their own purposes, they don't perceive it, they don't classify it in identical way. People have only limited and filtered access because the models are very complicated, they are very, very complex, and they need to rely on intermediaries, and typically the intermediary for most people are the mass media to communicate the results. And because they are, among other things, because they are so dependent on these secondary or tertiary sources to report them, they're also relatively easy to manipulate, so to speak. And people's perception, for example, you must have heard about this, that when you tell people, talk about global warming or climate change, everything else being equal, people react differentially to the same information depending on how it is labeled. And we found in a study a few years ago that this is particularly efficient. This framing or labeling effect is particularly effective for people who are in the middle of the political continuum. Not for people who are mostly on the right or people who are on the left and who are quite entrenched in their beliefs, but people who define themselves as being independent or unaffiliated with the major parties. And when you administer, the Six Americas type of classifications are the people that are in the middle. They are most susceptible than others to react to this framing. So now what makes the uncertainty in the climate change so special? First of all, it is the multitude of sources that are from totally different domains. So there's uncertainties about the physical phenomena, the actual science. For example, what is the actual climate sensitivity? There are uncertainties about things that are purely sociological and societal, okay? Like birth rates, policy decision, to what degree government are going to endorse, adopt, and enforce agreement that they make about policy. And of course, even if the government was to decide this is what we need to do, there is also there's uncertainty about how individuals or other entities, firms and manufacturers and so on, are going to accept and behave accordingly. And so you have many sources. The uncertainty in each one of these cases is of a different nature, and they need to be integrated and calibrated in a way that you'll be able to put it all together. So that's a very, very special challenge. And then there are multiple stakeholders involved in this process, the scientists on the one hand and everyone else on the other. And when they think about them, they don't necessarily think about the same components. They vary in their interest, they vary in their sophistication, and so they also make some assumptions about other things. And in fact, I'm going to talk about this in a second. So I think that from the scientific point of view, what the scientists' concern is mostly to be able to identify, quantify, map all the sources of uncertainty, put them all together in the context of the models. Then they need to be able to communicate them effectively to policymakers, the general public, who need to incorporate them in their own thinking and make decisions. And in some way, I'm saying that practically everything I'm going to say is going to be somewhat driven by this interface. So in other words, to how do we get scientific data and make it available and communicate it to others in ways that makes sense. So this is somewhat of digression, but this is something that I want to talk a few minutes about, a classification that drives my thinking about uncertainty in general. And this is work that Tom Watson and I have done many years ago. And essentially, our thinking about this is it's driven by a typology, if you want to think, but that's driven by three factors. Each of these factors or feature or attributes goes from precision at one end to imprecision or vagueness at the other. The first is the nature of the events that we are actually discussing. So one problem with communicating about uncertainty in general is that quite often people think they talk about exactly the same events, but they don't, because many of the events to which they refer are ambiguously defined, and therefore if different people think they understand, but that's really also only an illusion, that can lead to a lot of miscommunication or misunderstanding. So the first attribute is the nature of the event that can vary from unambiguous to ambiguous. Then there is the nature of the uncertainty underlying the event. And so there are many ways, there's a long literature about this and lots of ways to classify uncertainties, but the classic distinction is between what's called aleatory and epistemic uncertainty. And aleatory refers to things that are in the environment outside at least that's my interpretation, outside the control of the judge or the decision maker. They are simply capturing uncertainty that's driven by external forces. And typically, this can be mapped and can be quantified to the degree that it can be fully represented in a probability distribution. At the other extreme, epistemic uncertainty refers to internal perception of uncertainty. It is an inference about whether I have all the information, how complete, reliable, and is the information I have at my disposal that allows me to make my judgment. And so it is, as I said, internal, and it is quite often much fuzzier in its representation than the aleatory and the external. And so people have different ways of thinking and of combining these types of uncertainty. So it's, again, one could be precise and the other end can be very imprecise. The third component in this classification is how uncertainty is being communicated. And again, at the extreme precise end, we have using probability theory in its purest sense by saying this event has a probability of with a particular number. But then you have all these variations, intervals, linguistics, combination of those, and so on, which all signaling in one way or another some level of imprecision that is being communicated, and it is being inferred by the recipients of this information accordingly. But I think the most interesting and important part about this is that these two things, these three components, are not independent of each other. In fact, the principle of congruence that I'm proposing here is that people expect a match between the nature of the event, the type of uncertainty, and the way it's communicated. So if someone tells you that the chances of an abrupt drop in the market in the near future is 0.231, it's a weird statement. Why? Because abrupt and near future are ambiguous descriptions that can be interpreted differently by different people. B, because everyone who knows anything about the uncertainty that are driving the market, they recognize they're not purely aleatory, but have to do with a lot of temporary, transient, totally irrelevant things that cannot be quantified to the degree that would justify someone make such a statement, such a precise statement. So that's incongruent. Just the flip side of the same argument, saying the chance of drawing a queen from a deck of cards are low, is also inappropriate because it is a totally unambiguous event, because probabilities can be fully quantified, if nothing else, by enumeration, and therefore simply saying, all I can tell you it's low, is going to be disappointingly uninformative in the context of what you expect to see. So the principle that kind of drives much of our thinking is that uncertainty should always be communicated in a way that matches the nature of the events and their uncertainty. And let me put it further, it should be communicated always as precisely as the definition of the events and the uncertainty warrant and not beyond that. So first of all, I want us to a myth that permeates much of the thinking, I think in many decision contexts, is that people are always strictly dislike and avoid and hate uncertainty. And much of it goes back to Ellsberg paradox, and I want to make the argument that maybe this is a little exaggerated. So do I need to explain Ellsberg paradox? Is anyone here who doesn't know what it is? Okay, thank you. Okay, so in 1961, in his dissertation, then published in the Quarterly Journal of Economics, Daniel Ellsberg, the famous Daniel Ellsberg of the Pentagon Papers, right, proposed the following thought experiment. He never did the experiment. Many other people followed up on that. He did the experiment. Imagine you have two urns, one 100 bulbs each. One is 50 red and 50 black, clearly specified. The other one has some kind of composition which is unknown. So there are 99 possible compositions of red and black, but you don't know what it is. Now I'm asking you the following. I'm going to randomly draw a ball, and if it's red, you win $20. Which urn would you rather draw the ball from? And most people say the one on the left, the one that, no, 50-50. 10 minutes later, I'm going to ask you again. Here are two urns. I'm going to draw one, and if it's black, you win $20. And again, people say the one on the left. So that doesn't strike most people as a paradox, because everyone can articulate within a minute or two why they would say that. It is a paradox in a context of decision theory. Because if you say that you want the one on the left for the red, and if you want the one on the red on the blue, you imply that you think that the probability of a red plus the probability of blue on the right are less than 1. So in other words, you reject probability theory that says complementary events that make up the whole sample space must add up to 1. So in that respect, it is a paradox. But the way people think about it is that basically they said that Ellsberg has basically pointed out, and many people have shown experimentally, that people are what he called ambiguity aversion. I think that was the wrong term. What he meant imprecision or vagueness. But people are universally reject imprecision, then they always like the more precise one. But that's true to some degree, but it's far from being universal. So this is just a summary of a study that we did many, many years ago, where people made many Ellsberg-like choices multiple times, repeated, and so on. So we were able to classify each person's choices as being either consistent with avoidance, which is the expected pattern, or being actually consistent, choosing one and the other, or neutral. And even a minority of people have just the opposite pattern of actually liking, choosing twice to go to the unknown ball. And what you see that although avoidance is the mode, in fact it is, but it's never more than 40%. And I think it's really a mistake for many of the models that I'm seeing being developed to say, as a rule, universally, always, you have to build in vagueness avoidance as a given. Here's a study that we did in which we wanted to illustrate this and several other points, which was a choice problem. And it's associated with climate change, although the word climate change were never used in the experiment. So what we did is we wanted to communicate to people, you are in a pattern where you can put bounds on a target probability, but you don't know. The way we did it in the lab, people came to the lab and there were a bunch of urns of this type, and they were opaque, they couldn't see the content, but they could hear that there were balls in there. So for example, we tell them, this urn has already 20 balls in it of white and red, but you don't know how many. And then there were very, very large other urns with white and red, and we told them, count 40 red and put them in. Count 40 white and put them in. So now you know there are 100, and you know there are at least 40 red because you counted, and you know there are not more than 60 red because you put 40 white in, and therefore you are in a situation where you know that the probability of drawing a red ball is somewhere between 0.4 and 0.6, but you cannot be more precise than that. So that's a way of simply forcing people to deal with, that the probabilities are not precisely known. And they need to choose between three options: a risky, riskless, and a reduced risk. So the risky one was the following. We told them, the red balls were negative. You didn't want red ball because you'd pay a penalty. Everyone was getting an endowment, I think $10 or $20. And then you sample two balls. If both are red, you lose all your money. So that's the risky. You could avoid risk altogether by agreeing upfront to pay a fine, F. And if you pay that fine, then there's no drawing, there's nothing. You simply give up part of an endowment and risk is eliminated. And there is a reduced risk. And a reduced risk essentially is it's in some sense like an insurance policy. You pay upfront a small fee, and then you do the drawing. And if you are in the unfortunate pattern of having two red, and then in the so risk of losing everything, by virtue of having paid that small fee ahead, you don't do that. You have a chance of another draw, and only if all three are red, then you lose all the money. So that's kind of the representation of these things, and people had to choose among them. So how is this driven? This was a toy example that we came up to say this is like climate change. Why? Because the risky is basically facing the risk and business as usual. The riskless is taking immediate, severe, painful. The word immediately is kind of a misnomer, but you understand. Cutting right now and so on, and then eliminate the risk. And the reduced risk is this idea that you can reduce them to some degree without eliminating them. So this is what the problem looks like. Imagine a situation where you know the probability of the undesirable event is between 0.20 and 0.80. And these are the expected value curves of all the three options that you have. This one, the blue one, is the risky. This is the riskless. And this is the reduced risk. And notice that in all these cases, there was such that over the domain of interest, there was not a dominant. There are various. So if you knew, for example, that the probability is 0.4, then it's quite clear that the risky is best and riskless is worse. If you knew the probability was 0.8, then of course it turns out that there's a case where it pays to accept the fine and so on. So if you know where you are, then it's easy to choose the optimal option. But the point is that you don't know where you are between 0.2 and 0.8. And there's not a single dominant strategy across all the domains. Okay? So how do people choose in these cases? So I'm kind of very, very simplifying. You can see that as the uncertainty, the range of unknown balls increases from 0.4 to 0.1, people are getting away from the risky and in favor of the riskless. But contrary to what universal dislike of uncertainty would suggest, it never goes more than the same 40%. So people still continue, even in face of imprecision, to like the relatively risky option. Now, here's another interesting thing, which I think is even more relevant to this point. We presented the information to people in various ways. Half the people saw what we call the display pattern. So that's a screenshot of what they would think in the experiment. And first of all, because it was relatively complicated and wanted to make sure that they understood exactly the problem, they went through this bunch of questions where they asked to answer to all the questions about the parameters to make sure they understood. And once they answered correctly about what's the fine and what's the lowest and highest probability, they would see, for example, in this case, what the implications of the three policies over all the domains. So that was displaying the uncertainty in its completeness and its full glory. And then they had an expected value calculator, where they could say, they could play with this and assume all kinds of probabilities, right? And then for every probability distribution, they would specify, you probably cannot read, but that's to say the expected value of option A is, the expected value of option B is, and so on. So in other words, all the uncertainty was being reduced by being summarized in the expected value. So if people had this experience of totally dislike of uncertainty, they should have embraced unqualified, with no qualification, and always the expected value calculator. Turns out that when people experience both presentation mode and then they have the option of choose one, the vast majority actually prefer the one that display the whole uncertainty, rather than the one that was obscuring it by calculating an expected value. So people explicitly wanted to see the imprecise information, the probability information. So this is an example from a totally different domain, just to show you that people actually, in some cases, not in many, like imprecision. So this is work I've done with some colleagues of mine at Illinois who are all in the business school. And it started by Ning Du, a former student and now colleague, pointed out to me that publicly traded companies, although they are not required by any regulation, at least not in the United States, many of them publish either quarterly and or annually forecasts of their performance in the form of an EPS, expected earning per share. And if you look at the way they communicate them, it's only less than a quarter. They say, we expect the EPS to be 10 cents. The vast majority use ranges to signal their imprecision. And, and most of them actually alternate between precision and imprecision. And when they do that, the imprecision is 3-to-1 more popular. And so we basically hypothesize that the reason they are doing it is because they think, they anticipate that that is the level of communication and that is the type of information that the public, in other words, analysts and investors, wants to see. Because that will be perceived, think of my three-way classification, to be the most accurate and appropriate way of communicate uncertainty. So we ran some experiments with MBA students, and whenever they had the choice of investing, okay, so here's what we did in the experiment. We actually took vignettes that were essentially excerpts from press releases of companies, took away all identifying information about what the company is, but it was a description. So this company is located in the Midwest. They manufacture telecommunication equipment. They have a business, $70 or $80 million a year. They've just announced that their EPS for the next period is. And then we manipulated in this vignettes just the way we communicated the uncertainty. And when they had the choice, most MBA students were more willing to purchase stock in a company when the uncertainty was communicated imprecisely rather than precisely. This was much more qualified in the sense that they didn't like any kind of uncertainty, but there was a kind of non-monotonic, there was a single peaked preference. There was a certain level of imprecision that was perceived to be just the right and just the most appropriate one for this purpose. So people have an expectation or a sense of what is the level of precision that makes sense and it's natural and is acceptable in this context, and that's the one that they favor. And indeed, when you ask these people to make ratings, in general, these kind of imprecise estimates are perceived to be more informative, more accurate, more credible. I just want to mention this. The last thing I need to mention in this section is to mention work by Susan Jocelyn at the University of Washington that goes one step beyond these things, because she's the one that I know that she shows how communicating uncertainty to a company forecast is beneficial. So she does a lot of work, I think, funded by or in collaboration with the National Weather Service. And she sets up a lot of experiments with scenario where people need to make decisions based on information about weather. For example, imagine that you are the person who needs to decide whether to put salt on the road based on the forecast for rain tomorrow, and you have a limited amount, you have a limited budget for that. You have to think carefully whether to do it just when it's most likely to be useful and not to, and so on. Or imagine that you need to decide whether to stop the ferries because of expectations of high winds, okay? And so when she compares situations where people make decisions based on simply the forecast, the probability of the wind exceeding that velocity is, or the probability of snow by tomorrow is, just the point, and other forecasting in which this precise probability is accompanied by confidence interval, it's 90% that it will be between A and B. People on average make superior decisions that in terms of expected values and expected outcomes when uncertainty accompanies such information. Okay, so I'm switching now to a different to a different topics, unless people have questions, comments. Okay. So it's a. Oh, I'm sorry.
When you said people make better decisions, how are you defining better? Actually happen?
Yes, yeah. Because if you run this experiment and you can calculate the expected values of taking various actions under various circumstances, then people get higher expected values when they are also presented the information about the uncertainty. That's what I mean. Okay, so there's something that. So the point of the next talk is going to be not all uncertainties are alike, and people are sensitive to a variety of things about uncertainty in a way which may be somewhat surprising and counterintuitive. And I'm okay. The reason I'm kind of always feel funny when I talk about that is because when you teach decision theory and talk people about probability and talk the axioms of subjective probabilities, one of these axioms is that uncertainty is uncertainty, and you can compare various uncertainties. And one way in which people estimate uncertainty is you compare a spinning wheel, a probability wheel that is 60% red and 40% white and so on, and you can adjust it, with who will win the elections. And you expect people to be able to meaningfully compare whether they would rather bet on candidate X winning the election, or if you spin that wheel, landing on white. So, and what I'm going to show you is basically that people, there are all kind of subtleties that go beyond that. So I'm kind of have mixed feelings about it, but I think that the data will speak for themselves. So this is how this is in the context of climate change. People read, this is one of 3 or 4 scenarios, but the one that had been the most effective for us. Essentially tell people the ports in Southern California have a problem because in the not too far future, because of the ocean rise, they will need to basically re-engineer and to be ready for the higher levels. And so they need to decide, they need to make decisions. And the key argument here is that there is agreement about this outcome. There is some disagreement about models and experts who use the models on the timeline and severity of the problem. Okay? And so in order to deal with this problem, what we do, you go to 2 experts. And now the 2 experts can, and later on we also do this with 3 experts. That's more complicated. I will not show you that. But here's what the 2 experts could tell you. In one case, we could have one expert say 20 inches and the other one 40 inches. So that's really, each one of them is precise, and there's a conflict between their assessment. You could have 2 other experts who say it's between 20 and 40. They agree, but they are very imprecise in their statement. Or you could have one expert says between 20 and 30, and the other one says between 30 and 40. Now, imagine that you are the chief scientist who gets this information, and if you want to talk to your CEO, so what have you learned? Numerically, you say, I talked to 2 experts, and they basically told me it's going to be between 20 and 40 inches. So numerically, you are getting the same final result, not less than 20, not more than 40. But the point is that these 3 patterns are not processed and identified, or they don't have the same impact on behavior. And so the key result here that people have found before, and we're going to replicate, is that people are more averse to conflict than to imprecision. So that also, so first of all, it's just a distinction, which I think before reading these papers, I don't think I had this intuition. I think most people don't. And you can explain why that is, but probably because people, if you think how uncertainty can be resolved or reduced, it's much easier for people to see how, if multiple experts agree in this particular range, with new information, more effort, this could be reduced, than it is to see that 2 people who take diametrically opposed or distinct opinions are going to be able to converge on that. So we ran experiment, and so for example, if you were in a subject in our experiment, you would have seen something like scientist A used this particular model to project the increase, and that's what he said. And scientist B used this other model, and so on. I'll say something about the models. These are not real models. These are models that we made up, but we used permutation of all the right words, so to make up hypothetical or fictitious model. And they needed to estimate what's the most likely increase and to estimate the range. And so what you find, so in this graph, 10 and 40, this is what the two experts said, but in different ways, imprecision, conflict, and hybrid. And these box plots are essentially summarizing the judgments of the people who are in this condition. So what you see in imprecision, when they both agreed that it's going to be 10 and 40, the median of this distribution are precisely, they basically tell you back what, essentially what the expert told them. But in the other conditions, the estimates are moving closer. People are getting away, towards a sense of compromise, and this compromise is most pronounced in the case where they have a hybrid presentation. So they don't react to all these patterns, to all these three patterns in the same thing. When they're offered the possibility of buying insurance, and we're often the possibility what they are asked to say how confident they are in their estimates, it's in all these cases, people are basically are willing to pay more. The thing that they want to avoid most is conflict, and the thing that they actually are most comfortable with is imprecision. I'm going to skip this, but after they make all these choices, we ask. That's what this display was. Basically, so you've seen three different sample projections, and here's a reminder of what you've seen in each and every case. And do you ask people to say how precise were these projections? But we asked not only about precision, we ask about precision, ambiguity, completeness, informative, credible, easy to reconcile, accurate, and so on. And these are the ratings that we get in this exam. This is based on about 150 people. Then we replicate in a larger experiment with almost 1,000 people. And what you see consistently, or maybe you don't, is that the thing that is rated, the ambiguity is, ambiguity is imprecision, I'm sorry. The conflict is the least, is the one that people rate the lowest. It's the least complete, least informative, least credible, and so on. The one about imprecision is rated higher, and this is the hybrid, which is just in between. So another interesting that we did, another that was part of this study was the following, because we are following on some work of people who do models and they talk about uncertainty in models. You talk to modelers and they'll tell you, well, there are differences between models, and in models people have choices about how to parameterize them, what their initial conditions. And every modelers know that you need to, they talk about, I think, the internal variability is one of the ways to describe it. You need to run this multiple times in order to be able to get a sense of the ensemble and so on. So what we did, in other manipulation that were built in this experiment, people were told, the two scientists use the same model or use different model. Or the two scientists use the same model and they ran it twice under the same initial conditions or different conditions. And that's something that was basically completely ignored. No manipulations about whether the scientists use different or the same models and how many initial conditions they want. Nothing of that had any impact at all. This is part of something called a system neglect, which many people, not many, some people in the field have documented, is that when you have a system that's relatively complex, the thing that attracts people's attention are the surface feature. What people remembered, what they were sensitive to, were they in conflict, were they imprecise, and so on. And all the details about not how many models, how many parameters, and so on, were totally ignored. So what I've shown you so far is that people prefer precise information. Overall, people prefer precise information, but I think that the point about universal preference for precision is way oversold. People are sensitive to the nature of the event, and they have different expectation about this, and I think that this congruence principle captures it well in the sense that people have different expectations of what level of precision for various situations depending on the context and the nature of the problem and the events. And they also expect this to be communicated in a way that's consistent with these events. So I have now 12 minutes, and you didn't interrupt me, so I can stop here and take questions, or I can take 5 more minutes and talk about this work that, whatever. You tell me what to do. Or I can just go home.
No, don't go home.
Okay, okay, all right. Okay, so everyone knows what the IPCC, in this room knows what the IPCC is, and you may know that the IPCC has this rule about how to communicate uncertainty. This table, there's a document that's distributed to every author, reviewer. This table is part as a footnote or as an appendix, so every single report that the IPCC is issuing basically says, very likely, I mean, if it's not over 90%, you say very likely and so on. So I think this is there's a long history to that, and some people are writing some very nice histories about how uncertainty is communicated by the IPCC. And this is essentially a reflection of the principle I was describing earlier. Why don't they say 63%? Because the uncertainty is of the type that doesn't lend itself, honestly, to such a precision, right? So this is there's also a way to deal with the fact that in the various working groups of the IPCC that come from different disciplinary backgrounds and histories and traditions, people don't think about uncertainties alike, and that was a way to say, let's find something that can make sense to everyone. But we've been doing work on probability words for many, many years before there was an IPCC. And so there are lots of, there are some results that we can document. People's verbal, internal, personal, subjective lexicons of how they describe uncertainty are stable within individuals, but they vary widely across people. So your likely is my probable and vice versa. Interpretation of this term is subjective, is subject to self-serving interpretations and sensitive to context. So I was on a dissertation committee of an accountant, David Piercy, who basically essentially said, imagine you're an auditor, and the auditors are facing exactly the same problem, and they do the same assessment of the same material, but they are told, the partners really value very much this particular client. They would like this to be done quickly and effectively, or they were given a more, objective truth, spare no expense, and under different type of very, very subtle, well, maybe not very subtle, subtle motivation or push-up, people, the same auditors, interpret the same probability words in different ways that match, that's what I mean by self-serving, that match this. So the point is that if you think that everyone understands words the way you mean them, then you may think that communication is really no problem. That's what creates an illusion of communication. So it is in this context that we started doing this work to see whether indeed people understand the communications from the IPCC the way the authors intended. And one point that we immediately made, it's not a good idea to use only words, but we propose to use words and numbers. Why? Because if you use both words and number, then you appeal equally to everyone else, to everyone in the audience, the target audience, because people have different preferences of their own. And it's basically at no cost. It's a minute change that has no cost and very easy to implement. So we ran a study in which we took, essentially what we did is the following. We picked up 8 sentences from the IPCC, 2 with the terms very likely, 2 is likely, 2 unlikely, and so on. And then we presented people with the sentences, and we asked them to tell us, what do you think they intended to communicate? What do you think was the lower and upper bound? And the only thing that we manipulate in the experiment is whether they just saw the IPCC table and the text as it is, or the one that we were proposing where words and numbers are shown together. And then there's some other thing that we did with, demographics and, and some surveys and so on. And okay, so this is, if you are in the condition, in one condition, you've seen this sentence from the IPCC, it's very likely that hot extreme and so on. And then you had to move this slider to say, what's your best estimate, the max and the mean? And if you said, I don't remember the guidelines, you could click on there where it says click, and then the table will pop up, and then you will go back and you judge it. In the other condition, the only change was that whenever it says very likely, it was very likely in parentheses greater than 90%. Okay? That's it. Everything else was the same. So we ran this study. I'm still amazed that we managed to get all this. Never got a grant from NSF where 80% of the money immediately went to a company that did a sampling in 27 countries, in 18 languages, I think, because we ran this experiment all over the world in many, many languages with translation and back translations and so on to see how people because we hypothesized that people that because probability words are different in various languages, people would react to them differently as another source of confusion. So here are some results. First of all, people's interpretation is extremely regressive. Much more, by regressive I mean closer to 50% than intended. Look at very unlikely, which is supposed by the IPCC definition to be less than 10%. And these are the judgments of people of very unlikely, and you see the means and medians are in the 30 and 40s. Look at very likely, it's supposed to be over 90%, the mean and the medians are in the 70s. So what you can see that in each and every case, having the words and numbers together are pulling the distribution in the right direction. Downwards for these words, upwards for these words. Another way to see the same results is to look at how different are the estimates for very likely to very unlikely, okay? And this is a joint distribution when what's the mean estimate under the translation and verbal and numerical. If there was no difference, everything would have been on this diagonal. Since everything is above, it basically means that when words and numbers are presented together, the words are better differentiated, the terms are better differentiated as intended. In fact, this is the degree to which the proportion of estimates that are in agreement with the IPCC guidelines changes by simply putting words and numbers side by side together in the same word. Okay? So is this something that happens in one case? No. This happens in each and every one of the samples that we cast. In every single case, the bar on the right, which is words and number together, is longer than it was in the original condition. Here's something even more interesting, which again I didn't expect. Here what we did, we have 25 samples from 25 countries, and we have 4 words, very unlikely, very likely, and so on. So we can calculate in each and every case. So there are altogether 100 distributions of judgments. You can calculate how close they are to each other. And this is a mapping of all the 100 words. So you see, these are very unlikely, these are likely, and so on. So you see that there are 4 clear clusters, each one of every word in the different countries. And this is when you just show them as the IPCC does. But when you're showing words and number together, you have the same 4 clusters, but they are much more clustered, right? And better differentiated, much less confusion. So by using words and number together, you also make communication between the Korean and the Belgian scientists or whatever, better and more effective. So, so as I said, so clearly this dual scale is superior. And so I'm going to take 2 more minutes to show you one other thing, okay. So this is work that was prompted, Emily, who is a graduate student of mine, David Mandel and Mandeep Dami are psychologists who've been working for many, many years in Canada and the UK, respectively, with intelligence officers. And intelligence community has exactly the same problem. Because when people need to communicate what's the probability that, this terrorist group is going to do that, they also like to use words, and every intelligence community has its own list. Likely means, unlikely means. So everything about climate change applies equally well in that context. And so we looked at situations, and we realized that where does this scale come from? These scales come from several high-level people getting together and deciding, well, in our world, likely is going to mean whatever. When I first started working about this, and I asked someone to give me the data the IPCC used to come up with the table, people laughed at me, saying, what do you mean, what kind of data? We are scientists, what do we care? So there's no data, they're just made up. In fact, if you look at the number, essentially what you look like a normal distribution, plus minus 1 standard deviation, plus minus 2 standard deviation. That's how the determination was made. That's how words are interpreted psychologically. So what we basically said, if you look at this data, you should be able to essentially come up with cutoff points, so a binning procedure as to what to call likely, very likely in a way, empirically based on evidence that will be naturally much, much more accurate than the arbitrary one that was made. Okay? And so let me give you an example. So for example, if all you ask people, what is your best, what's your best estimate of very likely and very unlikely? These are two words that are similar. This is the distribution of best estimates of very unlikely, the red one, and this one is the very likely. If you have these two distributions and you find their crossing point and you say everything to the left of 0.22 or whatever that is going to be very unlikely, and everything above is going to be unlikely. That is not an arbitrary, but it's an empirical way of cutting points. This is based, reflects what people's natural thinking about these words are. And so when you're doing this, you get different cutoff than the IPCC. And in particular, you can see that under our procedures, I don't have time to describe the various procedures, the key difference is that the extreme words, very likely and very unlikely, cover much larger terms and much closer to the center. So we've done this procedure by using the data from the study that I described you, but using the US judgments as basically to determine these rules, and said, let's now apply this to other English-speaking countries. So we tested how well it works by using the UK and the Australian sample. And what you see is that where the baseline was that in the UK, 27%, and the Australia, 25% of people in natural judgments were in line with the IPCC guidelines, our procedure of using this empirical rule increased this from the 27 to the 40, so almost double the impact. So the bottom line here is that empirical research, empirical psychological JDM-oriented research provide sometimes important and sometimes subtle results and differences. And some of this, what's common wisdom, what makes sense, and so on, is the problem with common sense is that it's not very common, and so I think that people are, that's what makes sense quite often is really wrong and can be improved considerably by relatively minor judgment. So I'm running out of time, so I'm just going to leave this on the board, and you can read some of the recommendations that follow from some of the things that I described. Thank you. How difficult? So the IPCC, so first of all, that's interesting. This can be answered at several levels. So conceptually, it's difficult because different cultures have different way of thinking about uncertainty. So it's it's again widely known that, for example, in Far East societies, China, Japan, and so on, Korea, the way people think about uncertainty is different and so on. But practically speaking, it was not difficult at all. So IPCC is a UN body. Everything that they published is already published in the 5 official languages of the UN. So for these, there were translations. But the translation that they were using are purely dictionary translation. And the way we did it, we basically, I had collaborators in each one of these countries, and they hired people who did translation and back translation, and that was not difficult at all. That was very easy to implement. Yeah. Okay. Okay.